All right, people. Thank you. Thank you as always for being here. Finally, we are face to face. Sorry about the interruption of our classes face to face the last week. I was teaching for another organization, so it's a non-profit organization. So what we do is to try to expand the gospel of distance. That's what we do. So hopefully you watch the videos or you try to solve some parts, right? I believe I gave you a little time for that, but if it's not a lot, let me know, I can give you more. It's fine. I just want you to do it by yourself at your own pace, right? Every person learns at a different pace. So that's the idea of having something to do at home as well, right? So try to do it. And also in practice number 2, and actually I should open that one second here just in case. It might not be clear in the video. I was very tired when I recorded the video. You can see my face. But yeah, sometimes I record at night. Very late when my baby falls asleep and there is silence in my house. So yeah, that's how I do it. So sometimes I look like very tired. I don't even pronounce English very well, you know. It's like, I'm like, oh man, what kind of language are you talking there? And let me just show you here. One single thing. I believe it's here. So I hope you noticed that you can manipulate code in this practice number 2, right? You saw that you can run the code inside the web browser and change whatever you want, right? And then run the code again by clicking run code here, right? So let's imagine that you don't have R on your computer. You could use the web browser for that and solve all the questions that I have asked in this practice. For some reason it doesn't work, right, in your computer, you can use the web browser, right? Which is kind of nice, right? I need to update all my practices by adding this virtual R session, but little by little I'm updating most of the practices and assignments. But it's kind of neat. But what I wanted to tell you was, here, let me just do something like this. Is about these special topics part. Probably a little bit more advanced. And when you saw this, you were like, this guy really is adding a lot of complexity on top of more complex things. Well, I do that sometimes because I believe that some of you will understand this now, or probably later. I don't know. You might come back later to these lectures. You might come back later to this material. I don't know. I'm not teaching you for stats only for this program, but even for your life if you decide to be a researcher. So I will add some things that sound a little bit more advanced, but they're not. It's just things that nobody has explained very well probably to any people. So in this part, I didn't explain one thing here, or I tried, but it was not the best on the video. So let me explain you more about this example. In this part, I'm talking about missing data, right? In this part, if you watch the video, you saw that in R, missing data is represented with NA, right? Which stands for not applicable. That's what I mentioned in my video. Right? It's not a very good label in R for missing data. It's not intuitive, but they decided to call it like that, NA, right? And there is a problem in research, in statistics in general. When you have missing data, you have less information. So you have more uncertainty in your model, right? Because you are missing information. Missing information is always bad because you need that information in order to make inferences or in order to solve your parameters. I will explain later something about standard errors that will make sense later about these missing values, but in simple words, missing values are bad because they add more uncertainty in your models. So it's a pain when you have missing values. For example, if somebody forgets to answer 5 of your questions, and your scale has 10 questions, well, that's a big loss for you, right? So you have to guarantee that everyone answers your questions, right? The thing is that, as you read here, many people do things that are crazy. Well, not crazy, it's just when students are learning how to conduct research, they make mistakes. And those mistakes will actually drag the whole results to the trash. For example, at the undergraduate level, it's very common to see people using zeros to replace the missing values, right? You never use zero to replace a missing value. That I have observed that a lot. You might be thinking, "Wow, that's obvious. You cannot add a zero. That's not missing, right? It's a number, right?" But it's not that obvious because for many of us, well, for many of our students, they do the research. This is the first time you're conducting research, right? Well, at least the next semester is going to be your first time, probably, when you collect data and analyze information. So never use zeros to replace missing values. If something is missing, it's missing, right? Leave it there. That person didn't answer. Okay, just leave it there. The thing that we do in statistics is to create a label for that, and that's something that I explain later. And when you collect data, you have to assign a label for the missing values. Many times it's minus 99.99999 because it's a very big number that is unlikely to be observed among your values, right? So we pick some weird long number that's gonna be our missing value label, right? Now, the other question that people ask is, can I replace missing values with a mean? And the answer is no. So let's imagine that 5 people didn't answer the depression scale. But you are thinking, well, what if I use the mean of all the people that I have in the data set, the mean of depression, and I use that number inside that cell where there's this information, right? I can assume that the mean is a good representation of everyone, right? I could do that. And that reasoning is not that bad at all. Because it's true. You could assume, yeah, the mean value could be a good approximation of what that person could have had if that person answered. But the problem with that approach is that it will inflate your distribution. It will bias your distribution and your inferences, right? And that's what I try to explain here in this example. What I did in this example was to create a fake data set, right? As always, I simulated data. In this data, the real number for this slope is 0.2. The real number for this slope is 0.3. And the real number for this slope is 0.4, right? It's like, remember, when I simulate data, it's like I'm in charge of nature. This is my nature. And I can generate data thousands of times out of this model. And that's what I did. So what I did was to simulate, let me see how many. Let me see, 2,000 observations. I generated 2,000 observations, right? And after generating 2,000 samples with 100 observations, that's what I did. So it's like I collected 2,000 samples, right? So as you can see, the average value among all these observations, right, among my 2,000 data sets, is exactly the number that I specified. Of course, it should be, right? There's nothing wrong on how to generate the data, right? So once I take the average of all those replications, it's exactly the number that I set on the formula, right? For the case of the first slope, should be 1, right? Well, this is the intercept. The intercept is 1 right there, right? Then for x1, right here, should be 0.2. And on average, yeah, it hits the target. It makes sense because I'm generating fake data. But look at this. What happens when I add missingness to my data? And I replace the missing values with a mean. So in this second scenario, what I did was what happens if I simulate data that has missing values. And after that, I replace the missing value with the average or mean, right? So I did that. And look at that. This is the result, right? This yellow line shows that, this blue line shows that it deviates, that the average now is not closer to the real value. Look at that, it's a little bit far. And you might be thinking, well, it's not that far. I mean, it could be worse. Yes, it could be worse. But this is in a scenario where everything is missing at something that we call at random. But many things are not missing at random. So if you replace the mean, if you use the mean to replace the missing values, you're going to be far from the data generating process value. That's what I mean by data generating process. That equation that you saw there is my population model or data generating process. That's what I did. And we always want to be close to the data generating process. In this case, it's a simulation. I know the data generating process. Of course, in real world, we don't know. This is like doing an experiment in a lab. Okay? You control everything. But in real life, things might happen a different way. In this case, I'm simulating one scenario, only one, where I'm missing values, and I use the mean to impute the missing values. That's how we call it. And it's bad, as you can see, right? You have more uncertainty. That's why you are far from the real value. And that was the main message of this part. And also, I did that because I wanted to explain you, don't use the mean. Don't replace your missing values with the mean. And there are other methods for that. But of course, we don't have time for that all the time for this type of advanced methods. But there are other methods that you can use for replacing or predicting your missing values. Because you could predict your missing values using what? Using regression, which is amazing. Regression can be used for many things. You can also predict what could be, or what is the most likely value that could have happened there if the person answered the question here, which is amazing. We can do that under the right assumptions and the right model. But of course, I cannot explain that here because we would spend a lot of semesters studying statistics. All right. Now, all these things that I explained was because I wanted you to fix in this exercise this code right here, right? So this part is not explained on the videos. That's something that you have to figure out by yourself. So you have to Google it. Or, as I said in the video, you could use any AI engine if you want to, right? That's valid too. So just find a solution for that. How you can solve that, right? Because in my code, I'm getting an A. After estimating a correlation, it's not working. So something is missing. That sounds fun because we're talking about missing data, so something's missing. You know? So yeah, something's missing because it's missing data. So yeah, you need to add something here. You need an argument here. And just Google it. You will find a solution, right? And why am I encouraging you to Google? Well, because that's how you learn how to program any programming language. By Googling, you know, that's the only way. You learn by looking at other people's code. That's how it works for everyone, right? And you will find a lot of results, actually, many of results to solve it. So take your time and try to find that later at home. And if you don't find it, well, I can solve it here for you, right? If you think that you don't understand, I can tell you how you can solve it here. Yeah, I just wanted to explain that part because I thought it was not clear enough in the video. What else? Yeah, basically that. Yeah, perfect. Do you have any questions about assignments or practice? No? Not so far? Yeah, so.
I'm working on it, but it still is confusing for me. I'm working on assignment 1.
Mm-hmm.
So I just, I guess need more practice with it.
Well, what is confusing? Let me just trying to.
I was getting to the second part of the assignment one,
Uh-huh.
and can't remember where I was at, but it was just it's still, I guess,
The second part.
yeah, the second part.
Right here.
Yeah, I think just putting it all together is just still confusing for me, so
Okay, do you mean like copying the code?
yeah.
Okay, well, for this exercise, you just have to copy this in order to open the data. That's the only thing you have to do. And then you run the code, and you will have the data in your working space. That's the
Okay,
only
I
thing
think
you
I
have
just
to do.
need to practice a little more on how to.
Yes, try to do it. And if you still have questions, of course, I can help you. That's why I'm here, right? So, but yeah, in this assignment, you don't have to download any data set, right? Everything's gonna be read from my online repository. So you don't have to download it. And I saw Camilo's hand, right?
Yeah, I have a question regarding missing data
Yes.
on the last
Perfect.
part.
Uh-huh.
How come we have to Google the missing to look up the missing data if we have RStudio, it's so advanced, and how come we can't use RStudio? Why won't RStudio let us know that there's something missing, and why do we have to go to an outside source to look at what exactly is missing? Because I believe that like RStudio is so advanced with the codes, trying to reading them and interpreting that they should be able to like. If you enter a code, it should say, "Hey, there's something missing." Like at least let you know something's supposed to be there right here, or at least tell you what's supposed to be right there. You know?
Yes. Well, that's right. RStudio could do that, but to be honest, there are not softwares that do that. There's not, at least right now, that will require an AI reading your data and telling you what to do, right? That's the thing. It's complicated to do that.
Yeah, because you could. I mean, I would imagine that you could troubleshoot and tell the system like, "Hey, troubleshoot this. What is missing?" And then it should tell you that. I mean, if it's able to do all these codes, these complicated codes, and read it and interpret all, I mean, like, it should be able to do that too.
Yeah, not even softwares with human interface, with clicks and little pictures, they don't do that as well. Because that requires a software that reads your data and predicts what's gonna happen in your code according to your goals. So you have kind of set the goals for the machine, and then the machine knows what you want to do, and then it will predict or try to predict where it will find something missing, right? So that's a lot of work for programming. It could be possible. That's true.
So if I'm understanding correctly, your instructions were to Google that code, enter it into Google, and Google will put up code similar to that, and then we have to compare it to that to see what's missing on this one compared to the other ones.
Yes, let me show you how you can do it. So, for example, if I go to Google and I don't know, I ask a question, how to estimate correlation coefficient? Yeah, sure, why not? Yeah, wait, but no, not like that. Hey, sorry about that. We're missing values. And actually, let's take a look at the first link. I don't want to support that. So they are giving you here one little hint. Look at that. For example, we can use this web page, or you can find many, right? Even Google has some hints on how to deal with that. Or Stack Overflow, right? It will tell you, and you can see the results from other people, right? Like, for example, in this case, they are using this argument in the function. You don't have to copy the code. You have to ask to Google, what is your question?
Okay, that's what I thought. We're going to cut page all out to Google, but that helps right there.
Now, there is something similar to what you want to do. And of course, ChatGPT and any other AI can help you with that. So let me see. Oh, I'm not logged in. Let me log in again. Thought it was logged in here. I believe I can use this one. I don't know that one. I thought it was already logged in, but let me use Google. I'll change it later. I don't remember my password with my CSU account. Yeah, sure. Do that. So in here, let's imagine you're using ChatGPT or any other AI. You could say, you can copy this code, only this part, and then you ask to the AI and fix this R code to include missing values in the estimation. And let's see if it works. Oh yeah, totally works. Look at that. And it tells you the answer. That's very similar to what you want to do.
Yeah.
That's why it requires an AI. And that's hard to program. However, there are very good advances or very good projects on that. Like for example, for programmers on something called GitHub, it has something called Copilot that was created by Microsoft. So when you are programming online, Copilot tries to guess what is the best solution for you to program, for example. So people use that because they want to answer faster what they need, right? And also some people are using it for teaching because it's useful when you have another source of information, right? So this is one way where you don't spoil learning. You are using the tool for learning, right? So of course you can use it, right? And Gemini by Google is free too, and Llama by Facebook is also free, so you don't have to pay for those AIs. I can paste the AIs on Canvas probably, and you can play with the AIs and you can play with the code. That's good. It's one way to learn. Actually, I wish I had that tool when I was learning R. I never had that, you know. I had the best tool that I had was Google and some forums that Google was giving me back then, 10 years ago, 11 years ago. So now it's amazing. And actually, I'm learning to program in other languages thanks to this thing, right? So you can do it too. And I think you raised your hand, right?
I think you just showed me.
Okay. Okay. So yeah, hopefully that answers your question, Camilo.
Yes.
Yes, perfect. And I don't know if there are questions online. Let me check just in case. Let me open the chat. No questions. People online, if you have questions, please, you can type it down or just open the mic. We can hear you. You will be like these mighty gods talking from our roof. So yeah, it's kind of nice. Okay, cool. So the last time, let's return to the lecture then. If there are no more questions about assignments, if there are more, please ask as many as you want, right? Well, let's go back to our topic about regression, right? So the last time I was talking about what is regression a little bit, right? I told you that a regression model is a conditional model. That means that Y is going to depend on X. A conditional model means that I have a variable that depends on something else. So we assume that that variable was produced because it depends on something, right? So that's what we are assuming in regression. Y exists because multiple x's or one x at least is there as a possible explanation for Y. And I gave you an example, right, with age and memory scores. So I told you that in the classical regression model, what we do is to say that there is a distribution for each level of x, right? So in this scenario, I show you let me just do it. I show you this distribution of memory scores, right? When people are 27 or when people are 5, right? But of course, we are assuming that there is a distribution of memory scores for people who are 1 year old, 2 year old, 3 years old, 50 years old. There is a different distribution of scores in nature. But of course, in our data, we don't capture all the distributions of nature. We can't, right? So what we do is an approximation to that. But we still are assuming there is a distribution of memory scores at each level of X, at each level of my predictor, right? I also told you last time that there are different models that we can run. I'm just going through a quick summary, so you can refresh your minds about it. Or probably you already watched this lecture again, once the practice, I'm not sure, probably you're bored. But in here, what I explained was that there are different regression models, and that's awesome, that's amazing, but it depends on the distribution or the shape of your dependent variable. So for example, when you have binary outcomes, like for example, survive or die, that's a binary question. That's something that we answer with a logistic regression. And I'm hopeful that we will have time to explain that in this class because I'm going very fast. So that's awesome. That's amazing. Oh, come on. It's going to be fun. It's going to be fun because it will give you more tools for your research projects and in the future for your thesis, right? Or dissertations. So this, I'm hopeful that I'm going to introduce the Bernoulli regression, or in simple words, it's also named logistic regression. So we are going to predict what's going to happen, for example, in cases of cancer, right? If they have good chances of surviving or not, right? Conditioned on or depending on different predictors, right? So we can do that here. I have some data sets that we can play with. And some of them are sad, some of them are good. Life is difficult, but data also shows that, right? And of course, there are other models. For example, when you want to account for instance, when you want to predict counts, right? We are going to use the Poisson regression or the negative binomial regression. And again, if we have time, probably this is the first time that I'm going to cover those contents in this class, and that's gonna make me feel very good about it, because I feel like you have more tools and more skills later for your seminars. Remember all the time, right? Models produce data. Data does not produce models, right? Tell me, please.
Do you use this stuff in your seminars?
Yes.
That you teach the 4000s?
Yes, but I don't focus a lot on stats in those seminars because I have to assume that people already know stats. So, but if I have a cohort of many people who are from my previous class, of course, I can make different things. What I do, and that's a good question. Thank you for asking that question. What I do sometimes, I do a lot of meetings with the working groups. In my seminars, of course, everything's in groups for two reasons. First, of course, we have to learn how to deal with other people and working groups. Unfortunately, I'm a psychologist, but I don't like working in groups sometimes, because I'm very individualistic many times. But I had to learn how to work in groups. And secondly, is because we don't have a TA in the class, so it's difficult to grade all the assignments. So if we create groups, that reduces the amount of time that we spend grading, and that would give a better feedback compared to be overbooked, to be burned out, and grading a lot of assignments, right? Those are two reasons why we do groups. So I have a lot of meetings with the groups. And for example, if one group is working on probabilities of success, for example, in this program, let's imagine that you want to evaluate what is the probability, or what is the perceived probability of getting a degree from this program, right? And you actually do a survey about it. Your outcome is going to be yes or no, right? I believe I will pass, or I believe I will fail,
In those cases, I have meetings with the group, with the working group, and I explain about logistic regression only to them. I do like a mini lecture for each group. That's my approach. Because they need to analyze the data, and they need to understand how to interpret that information, right? Sometimes, if the person who is in the group is somebody who took my class with me, that person is in charge of explaining to other group members how they can interpret the results. Sometimes they do that, right? So it depends. It depends. It's a mix of many things. Given that my approach is very different from other instructors, I kind of have to adjust a little bit the seminars in a way that I include more information. So that's what I do. I work with the group. I do a lot of meetings with each group in my seminars. Yeah. I also told you that you can use different names for the same beast, right? You can call your X in different ways, right? Remember that I always use the words like predictor, or I also use independent variable sometimes. And for our Y variable, I use the words outcome, and sometimes I use target. That's true. Or dependent variable. But you can refer to these variables in your assignments with any of these names, and I will understand, right? There are more, actually, there are more names, but you can use any name that makes sense to me in order to understand what you're saying. This is a representation that I show you about the conditional distribution of Y given X. So in this table, what I'm saying is that there is a distribution, a probability distribution for each level of Y, for Y at each level of X. That's what it means. So there's a distribution of Y when X is equals to X1. There is a distribution for Y when X is equals to 2. So this is similar to think about my example of memory and H, right? So Y would be memory, and X is going to be H. So there's a distribution of memory scores for people who are 5 years old, 6 years old, 7 years old, 9 years old, right? That's the assumption about how memory works in nature, right? In my example. But it is an assumption for any variable in the universe, because this is a model, and the model is talking about how the universe works, right? Well, at least that's what we think. We don't know the whole universe, but we believe that it's a universal state. I explained you about the function lm, right? And this is how we are going to fit the models. We haven't jumped into explaining how to interpret the regression. I will, for sure. But that's why we are here today. So for the regression lecture, I always use the dataset wage. Oh, and by the way, I don't know if you noticed, but now on my webpage, you can also download the datasets. If you go to my webpage on psyc3000, it says experimental methods and designs. There are like a few links where you can download datasets. So these are the datasets that we use in this class, just in case you don't have access to Canvas. You can just go there and download the data. I forgot to tell you that. I updated that. Now, this is my wage dataset, but it's not mine. I took it from another package. And we will use it for regression models. So this is how it looks like. In the previous regression, right here, what I did was to use H as a predictor of wage. And let me show you the table. Probably should start from there. So I know that the table looks ugly, right? I'm thinking it's a lot of information, a lot of numbers with a weird font, right? Well, R was not thought to be friendly. R was thought to be useful, right? So of course, it looks ugly. There are ways you can beautify the output. I can show you how, right? There are packages already programmed that will help you to make the output a little bit more pretty, right? You can do that if you want pretty. You can get pretty too about R. But it requires, of course, know what packages to use, right? But I can help with that. But in this table, we have several pieces of information. We have the intercept, which is the starting point of the line that we are going to study in this lecture and probably the next lecture on Thursday. There is a straight line that we care a lot, right? And that line, let me just do it here. That line has a starting point, or as we say, it has a height where it starts. And then, boom, the line grows, right? So the intercept is the distance from 0 to any point. That's what we call the intercept. I will explain more about it. And also, and also there is a number here that is the slope, and that's what it will tell you the rate of change. How faster or how slow is the change? It's like a real slope, from a mountain or a hill. It's very, very similar to that. And it tells you how strong is the relationship between your x and your y, right? I'm sorry, between your y and your x. In this case, it's telling me that on average, people start earning $81.70 in this data set. And then over time, right? And then as age increases, their wage increases 0.70 cents. That's what it says. So for 1 unit increment in age, wage increases 0.70 cents. That's what it says, that little equation there. That's the result, right? And this rate of change is not explained by chance. And forget about this. I need to update these slides. I'm going to update it later. Don't pay attention to this. This is the wrong interpretation. It was another data set that I was using a long time ago. Then I changed it. So just don't pay attention to this interpretation here. I'm going to change it for the real one. So in here we have the p-value, and it says that this relationship or this regression line is not explained by chance, right? Because this value is way, 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 way smaller than 0.05. Cool. Now, this is how it looks like in a graph. This is our regression line, that blue line right there, right? And all these dots, they are the real data. This is the observed data from the data set that we are going to use. So you can see the straight line here, and there is a distance here. The distance from the floor is what we call the intercept. And how steep is this slope is the number that we get in the slope field in the box, well, in the table that I show you. So as you can see, the relationship is not very steep, right? It's not a line that goes like this. It's more like towards getting flatter a little bit. There is a relationship between wage and age, but it doesn't look very strong in the graph, right? When it's very strong, your line, your straight line is gonna be steeper, right? But in this case, well, it is not, and that's fine. Also, you can see a lot of people getting a lot of money here, right? They are getting around $300 per hour. So those are very odd cases, very extreme cases. Yes, there are cases in the United States that have that amount of money. I don't have that amount of money, but yeah, they do. And of course, some poor people, mortals here like us, right here at the bottom, like many of us. Then some people that are kind of getting closer to get more money, like these people, right? Like this guy here is kind of moving from one social economic status to the other, right? Little by little. But yeah, so, but you might notice something here. The straight line is not actually a very good line from this data. If you check it out, it looks more like a U, right? Almost like a upside down U, right? Something that we call a concave function, right? It looks like that. And probably the straight line or the linear model is not the best model for this. And that's why you have to plot all the time the information. You have to create graphics in order to understand if your model is also fitting the data well, right? In this case, it's not the best model for this data, right? There are better models for this, and we will see it later. But first, let's talk about assumptions, right? This is the regression model that we're going to study here. And we call it, well, I like calling this the classical regression model based on wave-falling areas. And what we have, as I said, is an intercept. We have the slope right here, beta sub 1, beta sub 2, beta sub 3, or many more if you need to. And we have error. Now, the error in the model is something theoretical. You never know the error. We assume there is an error, but you don't get access to the error. The error is part of nature, but we cannot measure it. What we are gonna do in this model and many other models is to measure the residual, which is the distance from the line that you selected as the best line to explain the relationship. I will explain more about it too. But that error there is something theoretical. We cannot get it. The only approximation that we have is some sort of residuals that we get. But that's the best we can do as human beings, right? Of course, if you do a simulation, you can simulate the error and see how the model behaves with different levels of error. Yes, in a simulation you can do it, but in real life, no, you can't. The only thing you can do is to try to create a very good research project with excellent measures and amazing interviewers or evaluators, and then or an experiment that is almost so clean that the error is attenuated, right? So that's one way we try to decrease the error by just doing an excellent job in the research design, right? Oh, and this is y, right? This is our outcome. So in this, we are assuming that y is produced given the relationship that it has with x, right here, right? And x is our observed variable, right here. Well, in this case, this is the population model, or the data generating process, but it could be a small x as well. Assumptions of the classical regression model, and this is very important in order to understand the model. One of the assumptions, well, it's not an assumption, well, it kind of is an assumption because it's what we start with in regression. We believe that y is a random variable that was produced by the conditional distribution of y given x, right here, right? Oh, there's a question in the chat. Oh, thank you, Saria. In the model which represents the slope and which represents the intercept. In what model, Saria? In the first one, you mean? Sorry if I'm mispronouncing your name. In the previous one. Okay, cool. Let me just come back there. No problem at all. In here, beta sub 0 is the intercept. In beta sub 1 right here, that's the slope. That's the parameter that measures the slope, right? So these two parameters have names. Yes, I forgot to tell you. Thank you for the question. So yeah, this is the intercept and this is the slope. All right, so in simple words, the assumption is that y is a variable produced randomly by a conditional distribution of y given x, right? That's the main point. And how do we test this assumption? Well, by feeding the model. We feed the model and we see if there is actually a relationship between y and x, right? That's the only way we can test that assumption, by just running the model and see if there is a relationship. In this model, there is also something that we call a expected value. Every model has an expected value. Expected value could be the mean or something similar to a mean, to an average. That's the expected value. In this case, there is something called the conditional mean function. And let me go to a plot. This is going to be our friend for a while. And this is an assumption of conditional mean. And we assume that each distribution, each conditional distribution at each level of x has a mean. And there is a straight line that puts together all the means in this conditional distribution. So that's the assumption of conditional mean. There is an overall mean that you estimate in the model by getting all the means of all the levels of y given x. Like in this picture, remember that in here we have on our y-axis we have our score in one possible exam. In x-axis is our time studying, right? How many hours do you spend studying? So there is a distribution at each level of x, as you can see, right? So there is a mean here for each of these distributions, and there is a line that puts together all these means, right? That's what it means saying it's the conditional function. It's a function that will give you the overall mean across all these conditional distributions. And again, these distributions are theoretical. You don't have all these distributions that I showed in this picture in your data. What you have is randomly, probably, one value of, I don't know, you have one person that probably studies 0 hours and you have the score for that person, right? You might have some people who study 5 hours, probably not in your data set. But if you repeat again the study, you will get different numbers and different numbers and different numbers. But all these numbers were produced by the same model. That's the assumption. Every single time you collect data about this topic, let's imagine that, you are getting data that is produced by the same model. That's why we always say models produce data. The data does not produce models, right? So, returning to this right here, the conditional mean function is, in simple words, all these means together, right? And we assume that we can get the overall mean across all these means. It's like a grand mean, right? Now, the other assumption is about constant variance. And probably you're familiar with this already. Probably you are already familiar with this because we also mentioned this in the test, right? Remember that one of the assumptions of the t-test is equality of variances. We assume that the variance of both groups in the t-test is the same. It remains constant. That's what it means. So in regression, we are going to make the same assumption. We assume that the variance of, and let's come back to the picture again. The variance of these conditional distributions is the same. The only thing that changes is the mean. Is the only thing that changes. But the variance of people, well, the variance of exam scores, given that you study 0 hours, is exactly the same as the variance of the exam score when people study 5 hours. It's exactly the same dispersion of that distribution. Remember that variance is related to the standard deviation. What we are measuring is the distance from the mean. So what we are saying is that in nature, all these distributions have the same distance from the mean. It doesn't matter if you study 5 hours or 6 hours, it's exactly the same dispersion. And you might be thinking, well, that's a very strong statement. You're saying that the variability is the same at each level of X. That's crazy. And yes, it's crazy. It's a very strict assumption, actually. And many times it's violated because we cannot hold the assumption because the model doesn't fit the data using that assumption. But that's, again, another topic for another advanced class. But someday, if you take my master's classes, I can explain more about it. And I will be very happy to do that. Budget. One of the assumption is homogeneity of variances, right? Or homoscedasticity, or constant variance. Many names for the many thing, for the same thing, sorry. So that's a very important assumption. We are going to evaluate that assumption later in this class. There are different methods to evaluate that assumption. There are some tests that you can run, but to be honest, even the tests are not very good at telling you if we really meet the criteria for constant variance when you collect data. Even those tests are not perfect. So we don't know many times. Yeah, many things we don't know when we are collecting data, because we are working with estimated data, with observed data. And when you work with observed data, it's kind of hard to evaluate the model further. So, well, we try and we do our best. Oh, a very important assumption, and that's the most important actually. There is another assumption that we call the normality assumption, or I like calling it more like Gaussian distributed assumption, right? What we assume in this classical regression model is that the conditional distribution of y given x is normally distributed. So in simple words, at each level of x, there is a distribution. And each of those distributions we assume is normally distributed. That means that it will look like a bell shape. Most of the observations will be close to the mean, right? There are no outliers and everything's perfect. Again, very strong assumption. Probably not. Probably our model is not the best for our data, and many times it's not. This linear model is useful, but it's not the best. It's tremendously useful, but assuming linearity in every single case is wrong. Many things in psychology change in a different pattern. Like, for example, memory. Actually, or for example, stress. Stress, for instance, has a different function. There is a human beings, and actually this applies for many beings in a planet. We can tolerate some amount of stress, some amount, and then the body kind of shakes, and our arousal increase. Our activation in the nervous system goes up to the point where it cannot handle any more stress. Then all this activation goes down over time. It's more like something like this. The function goes like this, and it's something that is well documented across different fields. So if we use a linear model for something like that, you would be assuming that stress increases. This is stress, just imagine that, and this is time, right? You would be assuming that over time, you can handle more stress, which is not true, right? So that's an example of a function that is not a straight line, that is not linear, right? So many things in life, especially in psychology, are not linear. But do you know why we don't use nonlinear models? It's because people don't know how to use them. They don't know how to fit the model. They don't know how to interpret the model. And that's why I want to change these classes. I want you to learn more about regression in a way that you don't have to assume linearity. because you don't know how to assume another thing. You can assume many things, and you can test if your assumption is true or is false, right? That's the main point of this class. It's not even about stats. Okay. And assumption normality. Any questions about assumptions? Any question is valid here? Anything? Anything good? It's kind of clear, the assumptions? Yeah. I think that the picture helps, right? Yeah. And the picture with all the conditional distributions, I believe, it's kind of a neat thing. I need to create my own picture. Another thing that I should tell you, and this box is more for me than for you, I guess. When the assumption of normality is not a good assumption for your data, like the model doesn't fit the data, right? You can change that assumption. And that's when we use different regression methods or different regression models. In the case of predicting outcomes of yes and no, like survive or die, we don't use a normal distribution as the distribution for the relationship between x and y. We use other types of distribution that we call the logit link, and that's going to generate a logarithmic function. So it's going to be a log normal and log normalish distribution. It's a different type of distribution. So we use different probability models, right, in order to understand the data, in order to find the model that best fits the data. So the same happens in the Poisson and in the Poisson regression. We can use different assumptions about the conditional statement of y given x. And that's why we need to understand more regression models, because questions are complicated, right? And I should stop here and we can have a break. Yep. Let's come back and let's see. 11:05. Let's switch your legs. Okay, so I want to show you something here. It's just a tool that I want to share with you. I'm going to paste this, I'm going to add this link on Canvas. This is an online, kind of an online probability models calculator, something like that. I'm not expecting you to use all this, but it's just an example of how many possible probability distributions or probability models is the same name for different things, right? For the same thing, sorry. How they are related. All these distributions that I mentioned are actually related to one another. One if many of them are the derivation of the other, because as a nature is very complicated, and all these distributions they always share something in common. Right? So in this link, it's kind of nice because you could actually simulate data, changing the parameters. Let me just go faster. And this will give you the shape of the distribution in this web page, which is kind of nice. And there are examples here. Like for example, the beta distribution, it says, for example, the relative humidity for Auckland, New Zealand for the first 6 months of this year, blah, 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 was beta distributed, right? With these parameters right here, with these values in the parameter, right? So it's giving you examples on how we use different probability distributions to study different types of variables in nature. This web page is awesome. Of course, there is mathematics around it. You could skip it, or you could try to learn it at your own pace. But it's kind of useful. This is the probability density function. You will see the probability density function for every distribution. This is our famous normal distribution, right? This is the probability density function. This is how we generate data, right? And you can simulate data by just specifying different numbers here. And actually, can I move? Oh, yeah. I can move the numbers and it will continuously simulate data out of the probability function that you can see here, right? And also it tells you how they are related. Like for example, the standard uniform distribution is a derivation of the beta distribution. The Weibull distribution is the father of the exponential distribution. So it's kind of nice. Well, I like it. It's very geeky, but I like it a lot because I don't know all the distributions in the world. But sometimes I need to understand what is the best probability model for my data, especially when I'm publishing papers, right? So this graph is awesome because you can click and see how it looks like. It gives you examples. It's kind of nice. I like it. It was created by a statistician at the university, the Buffalo University, very close to between the border between Canada and New York. That guy created this webpage, and I like it a lot. I found it like 2 weeks ago, and it's just saving me time. So I'm going to share this in the on Canvas. You don't have to use it for this class. Don't be scared. You don't have to. It's just another resource that you have in order to see how complicated and how beautiful can be actually probability functions, probability models, right? How complicated it is, and also the questions that we have to ask about nature, how we capture it, how we capture the shape of nature and the patterns that we see in nature, right? So, and actually, this is not a complete list of possible probability functions. Probability models, and there are plenty of more possible models, but these are kind of the main ones that we use in most applications in science in general. But yeah, I'm going to put it there later on Canvas for the sake of this illustration, if you can see that. All right, let me just come back to correlation. All right. There is also another assumption, which is the assumption of linearity. Linearity means that we are assuming that, remember, we assume that there is a mean for each of these conditional distributions. We also assume that there is an overall mean for all these means. There's an overall mean. And all these means are tied together by a straight line. That's the final assumption. That means that linearity means that we assume there is a straight line that ties together all these means, right? That's why that line right there goes through the mean of each conditional distribution. Yeah, actually what I said is this is what I wrote here. This assumption states that the means of the conditional distributions fall precisely on a straight line. And that straight line that I showed you before has the form of intercept plus slope, right? So it's a linear function that has an intercept right here, you can see it right here, and a slope right here. When we assume linearity, and this is something that is important to remark, beta sub 0 is the mean of y when beta 1 is 0. What does it mean? Okay, I could actually estimate a model where y would be like this: beta sub 0 plus beta sub 1 multiplied by 0. If you multiply something by 0, it's 0, right? So that means that this model is estimating only the intercept. So this is actually a model. You might be thinking, well, that's weird. Well, when we do that, the intercept is just the average of y. It's the only thing it is. It's just like getting the average. Like if you're studying depression, you would get just the average score in depression. That's what the intercept represents in a linear model when beta is 0, when beta sub 1 is 0, right? That's something that we call the intercept model only. I will talk about later. But I'm actually put it here. I forgot. Just multiplication, yes. But that's a very boring model, right? That's a model that we actually don't estimate often because it's useless. It's just giving us the mean, right? So what we do is to add predictors, right? We add a value here. We don't normally use, let me just delete this part. How can I add this? It is. We don't usually multiply by 0. We have x sub 1 here. That means that we have a predictor, a variable there, right? So when we do that, here, when we add a predictor on our equation, beta sub 0 is the height from the floor, right, up to the starting point, right? So in here, this is our height. All this distance from 0 is the height, right, of this line where the starting point actually is located. And the slope will tell us how steep is the line, right? Steeper lines mean that the relationship is stronger. Flatter lines means the relationship is weaker, right? It's a weak relationship between x and y. Similar to the plots that we saw in correlation. Remember that it was adding a straight line when we were seeing correlations. I told you that that's something that we call the line of perfect fit. Well, this is the time when we're going to talk about the line of perfect fit that I show you in the correlations. And by the way, when you estimate a model with only one predictor, like this one right here, when you estimate this model, the value that you estimate here for the slope, that's a correlation. When there is not any other predictor in your regression, what you are doing is correlation again. Because correlation is the base of regression. That's how regression was worked. And it's not random because the person who created the equation was also the person who also created the equation for correlation. So of course, they are related. So correlation is a linear function. That's what it means. Correlation is a linear function, similar and exactly the same as a linear regression model. Both are linear functions. Now, there's something that I forgot to tell you. I always forget this. The slope is also the difference between these conditional means right there. The slope will tell you the average difference between these assumed conditional probability functions, right? So that number also represents that the average difference between these theoretical distributions. That's what it means. But we never do that interpretation when we report the results, actually. I don't know why. Probably because it's something that we assume and we don't care a lot, but that's something that should be mentioned when we report things. All right. Now, the line of best fit. I told you that there is a line of best fit, and I mentioned that when we were studying correlation. So that comes out of an estimation method
that we call ordinary least squares. This one right here. That's the most common method for linear regression, estimation method. You can also use another method called maximum likelihood, and maximum likelihood will give you the same answer as ordinary least squares. For brief, people call it OLS. So when people tell you, can you fit a OLS regression? Well, that's a linear regression model, right? There are theorems, and there are different theorems that will explain the main properties of ordinary least squares. And of course, as always, we don't have time to go to theorems, and I'm very bad at demonstrating theorems. I always wait for a mathematician to explain the theorem. But of course, we don't have time for that. But I'm going to explain you some basics of ordinary least squares. So, in regression, one of our aims is to find the line, the linear line, that is closer to the data. But that's hard if you do it by hand. If you do it by hand, or if you did it by hand, you would have to draw, and actually let me use this. You would have to draw multiple lines like these ones, and then you would have to measure the distance of each data point to the line that you draw. Then you draw another, you will draw another line, and then measure again the distance of the data points to the regression, to the line that you believe is the line of best fit. And then you do it multiple times, and then you measure with a ruler the difference between each data point and the line that you believe is the best. And then, after writing down all the distances, you select the line that is closer to the data. The line that on average will give you the solution that is closer to each data point. That's the line of best fit, the line that is closer to the data. And actually, it's exactly like that. Let me just show you here. It looks more like this. So what we do, oh, I hate that. I have to leave this. Okay, cool. What we do is exactly the same. What we measure is the distance from the line. And the line that has the shortest distance to the data, that's the line of best fit. But of course, in real life, we don't take a ruler and measure the distance. That would be a lot of work. In order to do that, we have calculus. The first derivative of the function will give you that solution. But again, we don't use calculus here. We're going to use R. R will give you the best line of best fit in a few milliseconds. You don't have to do it by hand. But basically, that's what calculus is doing, if you do it by hand. It's trying to find the line that minimizes the distance to the data, right? That makes minimal distance to the data, which is awesome. This is something that we use a lot for many things. Even what people call machine learning and artificial intelligence is using this notion. Because we knew about it not time ago. Artificial intelligence is just a statistics, but people call it artificial intelligence. But it's just a statistics. That's how I learned. Then, for some reason, people started calling it that artificial intelligence and machine learning. But, well, that's how it is. But yeah, this is a principle that is behind many things. It's even behind on how your cell phone works. Regression is the mother of all the things that we have actually in technology. And we use these models to predict many things. And of course, Amazon uses those models in order to predict what you want to buy the next day. When you see these ads and everything, they run these type of models in order to understand what is the best prediction for a person like you. You're saying age and you're saying a pattern of expenses, and then they throw a commercial for you on the Amazon app because they know that it's very likely that you will buy it. And this model predicts that, which is awesome. And at the same time, scary, because that makes you spend a lot of money. It's true. I mean, the model is good. Sometimes they recommend very good things to me. I'm tempted to buy more. In this example, what we have is the size of the spider and the level of anxiety, right? I took this from Field's book. Actually, I believe that book is also on Canvas. You can just download that book, I believe. I don't know if I put it there. I need to check. So I took this picture from Field's book, and you can see a positive relationship between the size of the spider and the anxiety level, right? The bigger the spider, the bigger the anxiety, right? Makes sense, huh? Now, this distance from the line of perfect fit that we measure is what we call residuals. And I believe I pronounced that well. I've been trying to pronounce the word better. So what I'm trying to say is this word right here. Let me see if I type it down here. Well, I can write it down here very quickly. What I'm trying to say is receipt. Yes. Residuals. That's what I started to pronounce. And why do I make a very big fuss about it? It's because the closed captions sometimes don't understand my accent, and it writes something like with L. And when people answer my assignments, they write exactly the same word that they see in the captions. So I'm like, actually, the first time that happened, I was wondering, where are these people getting this word? I was like, I don't understand. Then I watched my video again, and I was like, the closed captions was writing this with L, residuals. So I was like, of course, because the closed caption software was not understanding my accent. So that's why I made that effort. So it's residuals, what I'm trying to say, right? And by the way, I never deducted points because of that, of course. I'm a fair evaluator, I believe. So it was my fault. It was not their fault. All right. So these are our residuals, right? This is the variance that we cannot explain by the model. This is the leftover. So we are missing that distance, right? And how do we make it better? Well, by fitting a better model. There might be a better model that creates a line that is closer to those data points, right? So our aim as researchers is to find a better model all the time. Not better data, better model. Well, sometimes better data also applies, especially if you do a crappy job collecting the data. You need to do a better effort the next time, right? But yeah, that's the main point. Yes, please, please.
So the residuals are the data points that are not on the line?
No, the distance.
Oh, the distance.
Exactly. That's a good question. Yes, it's not the data that is a residual. It's the distance from the data. So each of these data, these dots, is information in the data set, actual observed data. And the distance from this line, this little dot, 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 that's the residual.
Okay.
Yes. And actually in R, in many, and also in all the softwares for data analysis, you can get the residuals of your model. You will get the estimate of the residuals. Yeah, actually each individual in your data set will have an estimated residual. So you can see how far is each individual from the line of testing. That's also another way to detect if somebody's an outlier, right? For example, if somebody was here, let me check. If somebody was here, very high here, right? The residual of this person is going to be huge, right? All that line that I drew there, that would be the length of the residual. So it would be a big number. So when you get the residuals from your data, you can see that, oh, look at that guy has a big number of residuals. So of course, that guy, that person, probably is somebody who has a clinical problem, right? He or she might be hospitalized or something. So her levels or his level of anxiety are very high, right?
Okay, so let me see what I did here. Yes. So in here, what we have in this slide is what we call the intercept model only. This is the name right here. And of course, the name, it was named like that because it's only the intercept. So in here, what we have is wage, right? And there is no predictor here. And you might be thinking, wait, but you have a number one there. Well, the number one is something that we call the link of the function. I don't have to explain that part. But in R, it's following the same mathematical formulation. So when you add the predictor, little tilde, and then 1, you are feeding only a model with the intercept, without any predictor. It's the worst model ever, because you're assuming that the best predictor for your outcome is the mean. That's what you're saying, right? Just the average is the best estimate for what's going to happen or what happened in the data, right? So in this case, given that there is no predictors, what we get is the average of wage. And if you don't believe me, you can estimate the mean of wage, and it's exactly the same number, right? Exactly the same. Now, you could also be thinking right now, why do we care about an intercept model only, right? Why do we care about it? Well, because I don't know if you remember the notion of null model and alternative model. Remember that the null model is a model where there is no relationship between variables. An alternative model has relationship between variables. So what we want is to find a model for our data that is far from that one. We don't want a model that is close to the null model, right? This is our null model. And we sometimes use it to see if our alternative model is far from the null model. And that's what we want all the time. We don't want to find null relationships. We hopefully find relationships that are not explained by chance. Now, in R, you can add a predictor, right? Using the function lm, the programming function, not the mathematical function. This is the relationship between age and wage, right? So age is a predictor of wage. Every variable that is on the right of this tilde right here is going to be a predictor. And if there is a variable on the left, that one is the outcome, right? So this is the same regression that I showed you before. So as I said before, in here, what we see is that the average wage increases 0.01 cents, right? And it starts at $81.70 on average. However, we already saw when, let me see if I have, right here. We already saw that these people are kind of outliers, right? These guys right here. So these will move the line towards being a little bit biased, given that they're getting a lot of money. And that's why the average probably is not the best here, the intercept. Well, that's how it is. Now, another thing that I'm saying here is that pay attention to the intercept, of course. The value of the intercept is now different. It's not the mean anymore, right? Because I have a predictor. So this number right here is right here, is the height from the floor, right? And here is kind of 81 something something, it's right here, right? And then the slope is around here, right? So, no, actually, not like right there. Let me just right there. Actually, the slope is around here, which is interesting. It's very tiny. The slope is around here.
very, very tiny. So that's what increases a little bit the relationship. Right? And of course, this is the line of the speed that I just estimated, and you can see it right here. Now, what is the problem with the intercept? The intercept is hard to understand when you have multiple predictors, especially if you have predictors with different metrics, with different range of values. Like for example, if you want to understand stress and or the opposite. Let's imagine that you want to understand the relationship between stress and depression. We know that when people get stressed, they get more depressed, right? We already know that. But there are multiple ways to measure stress. For example, you can get a blood test and measure the levels of cortisol, or you could do a self-report instrument where you ask people to report how stressed they feel, right? So these two measures have a different metric. It's hard to compare. So what we are going to do is to transform these variables into C-scores. Actually, we use the letter C to represent when we are doing a C-score. How do we compute that? Well, it's very simple. What we do is to take each observation in the data set, then we subtract that from the mean, and we divide that by the standard deviation. So in the case of, let me just get a little pilot here. Oh, that's nice. Vanishing pen. What is this? Oh, here. Sorry, I was doing some experimentation with this. A smart pen. What is smart? Ah, cool. Okay. Sorry. I wanted to see if one of these tools was the thing I was looking for. They were not. Okay. So let's imagine that you are measuring stress, right? And I have, I don't know, Camilo's stress, right? I have his score right here. So let's do C, right? This is Camilo's score. And I have the average score of stress of this class, right? I ask you how stressed you feel right now, right? And let's imagine that the score goes from 0 to 100 and you are right now on 50. You are stressed, but not too much. Probably in the middle, you're fine because you're relaxed here, listen to a very good lecture, you're fine. And then we divide this by the standard deviation of my distribution of stress scores. In this case, the standard deviation of all your scores, right? So I add here, let's call it like this, like sigma. And after doing that, I get the C score for Camilo, right? After getting this. So Camilo will have a C score. Now, C scores are useful because you are transforming the data. You are not creating new data. It's exactly the same data. What you're doing is changing the shape of the data. Well, not even a shape, it's the same shape. It's just a linear transformation. So what you are doing is centering the mean at 0, and the standard deviation now is going to be 1. So, or at least the standard deviation will go in units, right? Let me see if I have an example here. I should. Let me just delete this. I could write everything on the Word, but even that there are people online, that's why I make the effort to do this. So, let me see if right here. Perfect. So, let's imagine that I want a C score for H, right? So this is the distribution. This is the raw score, the original H in this data set, right? The minimum value is 18. The first quantile is 33.75 years old.
the mean is 42.41. But after transforming the data into Z-scores, look at the values. They're different, right? So for example, the minimum value is now located minus 2.11 standard deviations below the mean. That's how you read that when you transform this into Z-scores. In other words, you are transforming the data into a metric that is evaluated in terms of distance from the mean. So it is standard deviations below or above the mean. So the mean is now 0 because it's centered at 0. So every variable that you transform into a Z-scores will be centered at its own mean, which is wonderful. So it doesn't matter the metric of the variable. It doesn't matter if you measure stress using cortisol levels in a blood test or a self-report measure with Likert scales. It doesn't matter, right? Because if you transform it, all the variables will have the same range of values. They will go from zero to plus minus infinity, right? Which is awesome. And it can be read as standard deviations above or below the mean, right? Which makes sense, right? The minimum value in the distribution should be below the mean. That's why it's a negative value when I transform it. That means that the minimum value is 2.11 standard deviations below the mean, and the maximum value in the observed data is 3.25 standard deviations above the mean, right? That's how you read it. Now, it will make sense later when you start making more regression models, because I will give you other types of data where the metric is kind of weird, and you have to make interpretations about that. But you don't know anything about the data. Actually, I have a data set that will be helpful for that. I don't even know the values for that one. But you could still interpret the results. You could still say if the relationship is positive or negative, or if it's stronger or weaker, right? Let me see. I should have a plot probably to explain this. Okay, well, let's keep it up to here. I will give you a break. Let's finish here because I need to modify a little bit the report because I think I have better ideas on how to explain that. So let's stop here. And of course, if you have questions, please stay at the end. I can help you for sure with your assignments or computers or whatever I can do to help you. Of course, I'm going to do it. So yeah, thank you. Thank you, people.
I'm sorry.